Grade 12 College Prep Physics. We're looking at mechanical advantage and efficiency. Doing first a little review on the law of a lever. In this question, you've got a camper wants to mount a trailer on trailer blocks. One corner of the trailer is lifted by applying an effort force using a 3-meter steel bar. That means the whole steel bar is 3 meters, okay? And the information, we want to find effort force required. We know the load force is 1800 newtons. That's the back end of the trailer. And the distance from the load to the fulcrum, so that'll be DL, is 0.45 meters. We're asked to find FE. We're probably already writing out this answer, but just looking at the givens, we're given FL straight up, we're given DL. The thing to know in this question is that the effort force, because it's a 3-meter bar, the effort force is obviously the difference between 3 and how far the load is to the fulcrum, okay? So we know our DE, and we just sub in and solve for FE, okay? So that's the first little bit on mechanical advantage, or just remember, we're not on mechanical advantage yet, but looking at the law of the lever. So if we look at our primary purpose that we focus on in this course of a machine, there are lots of them, but the one we're concerned with is the idea of reducing force required. Oops, typo. Required to do a job. Okay, and so how I say we define, I guess we will define mechanical advantage. It's a ratio, and a ratio is just a divide of load over effort force. Okay. And so we call AMA the actual mechanical advantage. So this means that this is, how much benefit do you get out of using this thing? Okay, I'm just looking at the above example. Our load force was 1800 newtons in that first example, and our effort was said it had to be 317 or 318. I put 317, but anyways, in the answer, then your AMA is 5.7. That means that you get a mechanical advantage of 5.7. So you put in, you put in only 5. You get, for every newton you put in, you get 5.7 out. Okay, and for a machine to be efficient, and they're not all efficient. Mechanical advantage on the body, for example, a lot of our levers don't work very well efficiently, but when you design a machine and you're looking for this purpose, right? The purpose of reducing force, you want your AMA to be greater than 1. Okay. So what if, for example, the person actually, to get this thing to work, for some reason, levers, there's not very much friction, but usually most systems there'll be some friction, right? What if something happened, you actually you had to put in 430 to get it to work? What's your AMA? So there, again, it's just load over effort, and there your AMA would be 4.2. And so where this is getting to is that a lot of times what a machine is designed to do, so that lever was designed that you should only have to put in 318 newtons of force. But then sometimes, because machines get worn, it's always related to friction, almost always related to friction. You don't get in what you designed to, right? And so your AMA is less than you hope for it to be. And so that's why I did that example there. So just a little bit on how we get mechanical advantage in different machines. So a lever, by using a longer lever, we can keep torque constant and use less force. In a pulley, your force is applied over a greater distance if you figure a bunch of pulleys and your string's getting longer and longer, but again, you're reducing force. Again, a gear, same thing. Torque constant, longer lever, and an inclined plane reduces force over a longer distance. So every machine has a simple machine has a very specific way in which you get mechanical advantage. And they're designed for perfection, is called ideal mechanical advantage, and that's what you should get out of your machine. And then if you actually do measurements on what effort you put in, you can actually get actual mechanical advantage. So this, I'm going to move ahead if you need to pause so you finish writing that. But the idea of ideal mechanical advantage is if it was perfect, what would you get? And then we can find efficiency by comparing actual mechanical advantage to ideal mechanical advantage. So every machine has a different way of finding mechanical advantage. So for a lever, if you went and multiplied your effort arm divided by your load arm, remember that's just, it says ratio, but ratio is a divide, okay? So if you divided out effort arm over load arm, that would tell you ideally how much mechanical advantage you get out of it. In a pulley, it's how many strands are pulling upwards on it, or holding upwards, or pulling upwards. That would be your mechanical. So you have 2 upward pulling strands, then you get a mechanical advantage of 2, ideal. Gears is ratio of teeth, and again that's just a divide, teeth on the effort divided by teeth on the load. And on an inclined plane, it's the length of the inclined plane itself, the length of the ramp, divided by how high you lift something off the ground using that ramp. Okay, and we'll do lots of examples. You'll see what I mean. I'm going to move forward, and I know that you'll probably need to keep writing this. You can pause. Okay. So the other thing we want to calculate is efficiency. And efficiency is how well does the machine work compared to how it was designed. Excuse me. And so that's, 100% efficient would be if your AMA, your actual mechanical advantage, equaled the ideal mechanical advantage. Because that would be 1 times 100 or 100% efficient. No machines are ever 100% efficient. Levers are close because you don't have a lot of wear and tear on them. But say you've got a pulley here. Okay, we'll do an example of calculating AMA, IMA, and efficiency. So, say you've got a pulley, and we have to use 700 newtons, that's my effort force, see that? To lift a mass of 100 kilograms. So that's the mass of my load. Okay, and I want to find the AMA, IMA, and percent efficiency. So just looking at all these givens, what I have here, I just wanted to put down on the side here, the load force is always the mass of the load times 9.8, so it's 980. Okay, so I know effort force, I know load force, and it's asking us to find AMA. Well, it's load over effort. We usually the big number divided by the small number. So our AMA, if you put those in, is 1.4. So load force is 980 divided by 700. So we get 1.4 out. IMA is the number of upward pulling strands. So what we said earlier on the page about finding ideal mechanical advantage. If you look at it, this strand's pulling down, but these two are both pulling up on my load. That was the design of this particular pulley. So the IMA is 2, because I have 2 strands pulling up. So percent efficiency is AMA divided by IMA times 100. So 1.4 divided by 2 times 100, and it's 70%. And you know it's a good answer. Just put a check mark on it as a good answer because it's, it's something less than 100. It makes sense. If I had 120%, I don't know. It's not possible. I probably made a mistake somewhere, or I made a mistake somewhere if you get something greater than 100. Okay? So that's just a little example of calculating actual mechanical advantage, ideal mechanical advantage, and percent efficiency. Okay, and I think that's it for this video.